Hello everyone, I'm Zichen Zhang, a third-year PhD student at CPES. My advisor is Dr. GQ Lu. Our research interests include high-density electronic packaging of wide-bandgap power devices and evaluation of insulation materials for medium-voltage power modules. Today, the title of my presentation is Characterization of a Nonlinear Resistive Polymer-Nanoparticle Composite Coating for Electric Field Reduction in a Medium-Voltage Power Module. Here is the outline of my presentation. First, I will introduce the insulation needs for packaging medium-voltage power devices. Secondly, I will talk about the characterization of a material that we believe can significantly improve the insulation performance of the medium-voltage power module. Then I will briefly talk about some demonstration and validation of this material in a real medium voltage power module. In the end, I will summarize my presentation and talk about some future work. Silicon carbide medium voltage power devices have attracted a lot of attention recently. This picture shows the commercial silicon 6.5 kV IGBT power modules, one from Infineon, one from ABB. On the other side, it's the CPES 10 kV silicon carbide MOSFET power module. If we compare these two, we can see the advantages of the silicon carbide module. First, it features faster switching speed. For the silicon IGBT module, the switching speed is limited to lower than 20 volt per nanosecond. However, silicon carbide MOSFET can switch as fast as 250 volt per nanosecond. And second one is the higher operating temperature. Because the silicon carbide has wider band gap, it can operate at higher than 175 degrees C. However, silicon IGBT can only operate below 125. The third benefit is the higher blocking voltage of the silicon carbide medium voltage power devices. For silicon IGBT, it usually can only block 6.5 kV. However, for silicon carbide, it can block from 10 kV up to 25 kV. However, these benefits of the silicon carbide medium voltage power devices are also challenging the packaging and the material selection in these power modules. This picture shows the schematic of a typical power module. The power device is usually soldered on a DPC substrate. Wire bonds were used to form top connection of the device. The other electrical routing is provided by the metal pads of the substrate and the terminals. The rest space inside the package is filled with an encapsulant. It can be an epoxy or a silicone gel. The faster switching of the silicon carbide medium voltage power devices requires interconnects with lower parasitic inductance. People use wire bondless or double-sided cooled module to get rid of the thin wires to significantly reduce the parasitic inductance. The higher operating temperature requires more stringent material selection, especially for the die attach. During the last 20 years, we have been using the sintered silver to replace the traditional solder. The melting point can go up to 960 degrees C. It also has much lower electrical and thermal resistance. However, the biggest and the most unique challenge is from the higher blocking voltage. The insulation materials, especially the ceramic in the substrate and the encapsulant in the module, are facing much higher electric field and causing the dielectric failure. People use the partial discharge inception voltage to quantify the insulation performance of a power module. This presentation's focus is to improve the insulation without sacrificing other performance of the package. To improve the PDIV, there are some geometric solutions. The first solution is thickening the substrate. By having thicker insulation of your substrate, you can have lower average electric field in your power module. but actually it is not very effective. By doubling the thickness of the insulation, one can only achieve about 30% of PDIV improvement. Besides, it also increased the thermal resistance a lot, because the most part of the thermal resistance in the power module actually is coming from the insulation of the substrate. The other way is stacking substrate. Instead of thickening the substrate directly, one can stack a few substrates together to achieve more homogeneous electric field distribution in the power module. However, even though it is more effective, by doubling the thickness of the insulation, you can achieve about 50% PDIV improvement. However, it still increased the thermal resistance, and also because it involves large area bonding, it could cause some reliability or manufacturing problem. There are also some other geometric solutions, for example, protruding substrate and trench structure, and also some air pocket. However, they all have very limited effectiveness, and also they require complicated process. So there will be some cost and yield issue during the before they can widely accepted. Material solutions were also explored. Researchers are focusing on two groups of the materials. The first group of the materials have high permittivity. They are called capacitive field grading material. For example, barium titanate was filled in the silicon gel to increase the permittivity of the silicon gel. It was reported that his material can increase the PDIV of the DB substrate by about 30%. In this work, strontium titanate was filled in the epoxy, and to increase the packing density in the critical regions, electrophoresis was used to redistribute the fillers after the encapsulant curing. They were able to increase the AC breakdown voltage by about 60%. However, this capacitive field grading material usually need very high material loading to achieve high permittivity, which will make the material very viscous, and it could be a problem when you want to use it for encapsulating a real power module, because it will be easier to trap bubbles and cause partial discharge. Besides, they are only functional under AC excitations. The second group of the materials were called resistive field grading materials. Zinc oxide and silicon carbide were usually used to fill into the polymer matrix. As shown in this curve, they are more insulative under low electric field but more resistive under high electric field. We proposed to use this kind of material as a coating or shielding layer at the critical regions in the power module prior to the primary insulation, for example, silicon gel. We used the FEA simulation tool to model this kind of material and find the desired IV curve of the material for the medium voltage power module applications. Recently, there are some groups have demonstrated a similar concept on the medium voltage power module substrates, including us. In this presentation, I will talk about the material characterization, and also I will talk about the demonstration of this material in a functional silicon carbide 10 kV power module. In the next session, I will introduce the material and talk about the material electrical property measurement, PDIV test on the real DBC substrates, and some electric field analysis to explain the PDIV improvement. To characterize the electrical properties of this material, we made a few thin film samples. So this picture shows the Polymer-Nanoparticle Composite solution. I will just call it PNC later. So the material is received from NBE technology. To make this thin film sample, we use the spin coating process. First, we spin coat the solution on the gold-plated metal substrate, and then we cure it at 180 degrees C for 30 minutes to form this thin film coating. So we measure the thin film coating thickness to be around 20 micron. And then we did the PVD process on top of the coating to form a layer of metallization. This metallization will serve as electrode when we do the electrical characterization later. So, and then we use this sample to measure the IV and CV characteristics of the coating material. From the IV, we should be able to calculate the conductivity versus the applied voltage, which can be translated to the conductivity versus electric field. And for the permittivity is the same. We can use the CV curve to calculate the permittivity. Here shows the IV and CV results. So the CV test is under 0 to 100 DC voltage with a 25 millivolt AC bias at a frequency of 100 kHz. We got a field independent capacitance, which is 15.7 picofarad. And we can use the formula we showed in the last slide to calculate the permittivity. It's about 3. And then we use the IV curve to translate to the apply E field versus the conductivity. We can see the blue curve is the measured curve, and the red dot is the fitted curve. We use a formulation usually used in the references to fit the curve, and here are the fitted values. These fitted values are within the range we previously find in the simulation paper. So this should be the desired properties for medium voltage power module field grading applications. After we got the desired electrical properties, it's time to validate this field grading effect on real DBC substrate, which can be used for packaging power module. Here shows a schematic of the test sample. The DBC substrate is patterned with 2 mm gap between the 2 copper pads, and the alumina thickness is selected to be 0.38 mm. Here is the triple point. It's the triple point of copper and your encapsulation and alumina, which should be the highest E-field location according to the E-field simulation. Here shows the cross-section view of the real sample, and here picture shows a top view of a coated sample. To find out the field grading effect of this PNC material, we made samples with and without coating. We have samples with only silicon gel encapsulation. We also have this kind of coated samples. The black region on the at edges of the copper is the coating itself. So to have a closer look at the coating, we made some cross-sectional samples. We potted a DBC substrate after PDIV test into epoxy, and then we use a auto polisher to polish down the sample to the triple point plane. Here shows a zoomed in optical image under a microscope. Here is the copper, here is the alumina, and this is the putty material we used. It's the epoxy, and this dark region is our composite coating, and here is our triple point. We can see that after the chemical etching during the substrate preparation, we can see there's a sharp corner left here, which could cause very high electric field intensity concentration here. As I mentioned, we have 2 groups of the samples. One group are with the coating. We first coat the PNC at the edges of the copper, and then we encapsulate them in the silicon gel. Samples without coating were also prepared. This plot shows the PDIV measurement results of those samples. And for the samples with the coating, they have clearly much higher PDIV than the samples without coating. Coated DBCs have up to twice the PDIV than uncoated ones. And actually, during the test, we start to see some breakdown inside the alumina before the encapsulation failure, which means the alumina start to limit the insulation performance instead of the silicone gel, which is usually the bottleneck of the insulation for medium voltage power module. To understand the PDIV improvement provided by this PNC material, we did some E-field analysis to find out the E-field reduction effect of this PNC material. So this two pictures shows the E-field distribution around the triple point. The top one shows the triple point without coating, and the bottom one shows the triple point E-field with the coating. The simulated geometry is constructed based on the optical observation we showed in previous slide. So here's the copper, here's the gel, here's the alumina, and this thin layer is our composite coating. We use this measure line L to analyze to extract the E-field from the simulation. We can just look at this E-field distribution. We can see that after we apply the coating, the high field region, the red region, is significantly reduced. And to show more details, we can extract the E-field from this measure line, and you can see the plot here. So the blue curve shows the E-field along the measure line L without coating, and the red one shows the measure line with the coating. We can see that the highest electric field was reduced from 77.1 kilovolt per millimeter to 36.5 kilovolt per millimeter. So the measured material properties and the geometry were used in this model, and we found the E-field reduction about 54%, which matches the PDIV improvement we observed in the experiments. Now it's time to demonstrate this technology in a real functional module. Now I will just briefly introduce the packaging work we have done recently. Here shows the packaging design. It's a 10 kV silicon carbide full-wave diode rectifier. The diodes were sandwiched between the two DBC substrate and a metal post. All the joints were done by silver sintering. All the DBC substrate were coated with the PNC coating. The biggest benefit of this package is that we have PNC coated DBC substrate, which allow us to achieve PDIV higher than 15 kV with a much thinner ceramic, which means we will have lower thermal resistance and still have better insulation than the other medium voltage power module. Here shows some module testing result to validate our package design. Here shows the reverse blocking test. All the diodes were characterized after packaging. They showed identical characteristics after packaging. All four devices can block 10 kV at leakage current below 50 microamp. Here shows the rectifying waveform. The 9.5 kV peak rectified waveform validate our package design. So summary and future work. In this work, we processed and characterized a nonlinear resistive coating material and observed up to 2 times PDIV from coated substrates for medium voltage modules. We also validate the coating technology in a 10 kV silicon carbide full-wave diode module using the substrate with the ceramic layer at least 50% thinner than those used by others for making 10 kV power modules. Future work. We will validate the coating technology for packaging power modules with higher voltage rating. We will also need to evaluate the reliability and high temperature performance of the coating. Thank you for listening. Questions and comments.